All right. So it's 5:32. I'm going to get started here. Okay. So we do have lab tonight because we are going to start the actual second phase of this class. Remember, on day one, the first lecture, I said something about this is the great suspender, which is a great, excellent Chrome extension. It allows you to suspend individual tabs after a certain amount of time of inactivity. So in this case, I set up mine to basically suspend all the tabs after 15 minutes that they have not been used. And you can also set up which one you do not want to suspend, like the ones where you have a form partially filled in and not submitted. So it will know not to suspend those, because otherwise when you refresh, you lose everything that you filled earlier. So great tool if you're like me, with typically 20, 30 tabs on a browser. I know it's a bad habit. Okay, I cannot let go of tabs. Attachment issues. Anyway, so this is I was just working showing somebody else the extensions that I use in Chrome. And the design hub was working on something related to forms. So that's why you see all of these tabs, open, because, I have, throughout the day, I work on, completely different things, depending on what time of the day. And of course, it has a cute icon too. Now, in my case, if they can let me, if I find out which file that I can modify, I can have, okay, this is how you wake it up. So it's fairly pleasant, right? So with mine, it's going to be coffee, right? It'll be spilling coffee on it, and it'll go like, like that. All right. So what we'll do today is we are actually kind of moving on to the second phase of this class, which is getting into the programming part. So tonight's lab is more or less a way for you guys to get familiarized with the tools that we'll be using for the rest of this entire semester, okay? So there are several components to the whole thing. So I will go ahead and go to, so the lab activity for tonight is called familiarizing with the TTP toolchain. It's not released yet. You guys cannot see it just yet, okay? But I'm giving you a preview, okay? So the first thing you need to do, TTP, by the way, stands for Text Toy Processor, okay? Which basically is exactly what it is, okay? It's a toy processor for instructional use only. So the first thing you need to do is to go to a shared folder, which I shared with all of you from the beginning of the entire class, which is this one here. So I'm going to open it in a new tab, and that's why I end up with this many tabs, right? Every time I open something, it's always a new tab. So this is the folder, okay? Some of you might have explored here a little bit, some of you may not, okay? It's okay, either way is fine. So what you need to do, I'm going to do it here so that you kind of know what to do in the lab, is to download a few files. So ALU is one of those files. Let's see, processor 0003 is another one, and then regbank is another one. So these three files are the ones that you need in order to do homework from here on. Okay, so it's not really just for this particular lab. It's like, from here on, these are the files that you need. So right click after you have selected these files, control click will do it, and then just say download. Okay. So it will zip it first, and you'll be downloading a zip file. Then you can just unzip it on your side. This is not big enough, but it does remind me of one of the quote-unquote professors in Ruby. Does anyone watch Ruby from Rooster Teeth? No? Nobody does? Okay. No. Okay, so ttp.zip, I'm just changing the name. So now I switch back to my command line interface, and then we'll go to the temp folder and I'm just manually unzipping the file. You guys obviously know that Windows can do it without a command line. So it will unzip into these three files. So the way you do it is you start with processor 0003.circ. So you just start your logisim. The way I started here is a little bit more involved because it is all on the command line. So you guys probably can start it a lot easier than I do. Okay, and then you just give it the name of processor 0003.circ, or you can open up logisim first and then have it to open that file. And this is it. This is the processor. Okay. Now it looks kind of complicated, but it just looks that way. Okay, it really is not. So we'll talk about the components of this processor. Okay, and you'll be writing programs to run in this particular processor. Okay, how many of you remember those kind of V8 engines that has a transparent plastic housing when you were a kid? It's kind of like that, okay? Where when you turn the crank, you can see all the valves moving, all the pistons moving, and stuff like that. It's kind of the same thing, except it's not an engine; it is a processor, okay? All right. So this is the first part. It's just to download the files, know which one to open, and then the quiz will proceed to ask another question. After finding the missing, okay, there are actually no missing library files. You should open the processor file. So it has two main memory components. So we'll first talk about those two components in today's class, just so that we know what they are. This is one, okay, so let me just kind of highlight which one. I will use the selection tool. Okay, so this component is known as RAM, okay, because you can see that once I select a component, it says, oh, this is RAM. A RAM stands for Random Access Memory, okay? And what it does is it just stores information. The way it works is the address bits, okay, the A port, what you present to the A port is kind of what you put inside the square brackets when you access elements in an array, okay? Is that okay? And then the D port, which stands for data, is the content at the location that you specify. So let me say that one more time. What you present onto the A port specifies the address, okay? It's the address of a location in RAM. And then the D port allows you to interact with the content at the addressed location, okay? And it has a bunch of control ports as well. So of the control ports, we have the first one. This is SEL, or SEL. It stands for select. Most industry terminology would call this one CS or chip select, but select works too. So if this one is a 1, that means the component is selected, which means, hey, RAM, pay attention. Okay, that's what the select line is doing. It's analogous to the enable line of our D flip-flops. Okay, it's level sensitive. The second one, which does not have any actual name, it is only represented as a little kind of triangle, that's our clock line. It is also analogous to the clock line of our D flip-flop, okay? A rising edge means, oh, let's go ahead and store, okay? Whatever is presented at the D port, store that content to whatever the A port is specifying. The location is going to be specified by the A port. LD over here is the abbreviation of load. What it does is it controls, do we want to write to the RAM component or do we want to read from the RAM component? Okay? When LD is a 1, we are reading. When LD is a 0, we are writing. And then the last one is clear, which is analogous to reset of our D flip-flop discussion from Tuesday. In other words, hey, you can look at this as a gigantic array of registers where the A port specifies which register do you want me to access this time. Are we good so far with this? Not really? Yep.
You have a reset under RAM load, but it's not connected to anything.
So RAM load is connected to a tunnel called RAM load, which is kind of down here somewhere. Are you asking about this reset?
The reset, yeah, it's not connected.
Yes, because I don't want that reset button to be hooked up to the global reset button, because if you reset in Logisim, it will reset the content of RAM. You will lose all the content in RAM, which may not be what you want to do. So that's why the reset or the clear port of RAM has its own little reset button, so that it is not going to be reset unless you push that button. Okay? So is the general idea okay, of what it does? Okay? Now, what if you say, well, I still have no idea what what it does? One thing you can do is to go to Help, go to the Library Reference, go to Memory Library, and then click on RAM. So this has the full documentation that is built into Logisim, and you can read this part as well. So the idea is RAM is read-writable. In other words, you can overwrite content of RAM and say, hey, I want to remember this number at that location. RAM can do that, okay? But you can also read a location in RAM. It's like, oh, I want to go to that location in RAM and find out what is the content, what is the value stored at that location. So it's read-writable. Other than that, you can treat RAM as an array, okay? You have one way to control which location you want to access, which is through the A port, and then you also have another port that allows you to interact with the content at that location. So are we doing okay so far with the concept? More or less? Questions? No questions? Sorry? Data width. Okay, the width. Okay. So if you go back to here, okay, there are only 3 attributes associated with RAM. The third one, we are not going to deal with it, okay? So it is basically synchronous, and we'll just stick with that. The first 2 has to do with the width in terms of number of bits associated with the A port, the address port, and also the D port, which is the data port, okay? So what that is going to do is you can control the width of the A port. When you so that determines how many locations we have on this particular RAM component. So right now you can see that the A port address bit is set to 8, right? So we have 2 to the power of 8, which is 256 locations in this particular RAM module. If you make it 10, then you have 1,024 locations. If you make it 16, then you have 65,536 locations. Is that okay? Yeah.
0004, so that's the address?
So yes, so these are, so this is, so 00, this 00 is telling you the first item of the row is at location 00. So this 00 is the content at location 00. This is location 01, 02, location 03, location 04, and so on, okay? Now, you look at this and go like, well, I thought we have 256 locations. How do we get to the other locations? Because I can only see 16 of them, right? So the trick to do that is to right-click on the component, and then you select Edit Content. So this will give you an editor that gives you access to all locations in RAM. Is that okay so far? Okay. So you have to remember how to read it. The number or the hexadecimal number all the way to the left-hand side, that is the address. Okay, it's the address of the first byte of each row. So in this case, this is location 00, this is location 70. Now, if you work with a particular location like this, then you have to count, because the row itself starts with location D0. So we have D1, 2, 3, 4, 5, 6, 7, 8, 9. This is DA, because it is in hexadecimal, right? So after 9, we have A. So that's location DA in hexadecimal. So are we doing okay so far with this stuff? Okay? So the other way you can get familiarized with a RAM component, okay, so in this case I can just take this, okay, Control-C, copy it, and I'm just going to start a new file, okay? I don't even bother to use a new circuit, and I'll just paste it. Uh-oh, where did it paste it? I do a Control-C, but I have no idea where I put it. So let's zoom out. Okay, there we go. There, okay. Okay, so you can just kind of play with it. You can exercise, you can try different things. Like, the address bit does not have to be the same as the data bit. So you can have like 10 bits here, which means now we have 1,024 locations in this RAM. Now, when you look at the data bit width, it is 8 here, which is the default. That's because we typically want to work with computers that have a byte addressable memory. Okay, that's a typical way that we organize memory in a modern day computer. But it doesn't have to be this case. Okay, if you, for whatever reason, want to say, I don't want to have 8 bits per location. I want to have like 13 bits per location. Sure, why not? So now each location has exactly 13 bits instead of 8 bits. Yes? I believe so. Yep. Okay. So now how do we play with this? How do we get familiarized with the operation of RAM? Well, the address port is always going to be an input port, which means you always hook up an input pin to that thing. So you can experiment with a RAM component just by putting a, so how many bits do we choose to use? 10 bits, right? So we have to make it match the actual width and draw a wire from here to here. There we go. And then we have single bits for the select. Okay, select is always going to be an input pin also. So this is going into the select. And then we have another one for clock. Oops. These are control signals to a RAM component. And then we have another one for load, which basically controls, are we reading or are we writing? And then one for clear, which is basically the same thing as a reset. If it is a 1, then all the content of RAM is going to become 0. Data port is the funny one, because this is one that is bidirectional. In other words, for certain operations, it is an input port. For other operations, it is an output port. So that kind of makes it kind of tricky, okay? We'll deal with that problem later. And for now, we'll just assume that we are reading the content in RAM. So we'll have an output port associated with it. And it's complaining because the width is different. So you can see how it is complaining that it should be 13 bits wide. So we'll have 13 here. Okay. So now we have all the basic ports to access a particular RAM component, and we can start to experiment with it. You can see how the A port has a different width compared to the D port. Once again, A port is controlling how many locations do we have in this RAM. Since we have 10 bits, it's 2 to the power of 10, which is 1,024 locations. On the other hand, the width of the D port, which in this case is 13 bits, is controlling the width of each location. So each location of this particular RAM component has some really oddball number of bits, which is 13, okay? But, hey, if this is what we want, this is what we can get. So now the question is, how do we, work this out? So I'm just going to go ahead and inject a value into one of the locations. So the way you can inject a value into a location is just to click on it and then just start typing in hexadecimal. In this case, because it's a 13-bit wide kind of content, we can have anything that goes from all zeros to basically 13 ones. What do you guys want to put into this location? In hexadecimal, correct. You cannot have, no, because there are 13 bits. Right. There are 4 bits to 1 hexadecimal digit, so you have 2 3/4 of hexadecimal digits. 1 F would be good, but I cannot have 1 FFF. Because 1 FF has 3 hexadecimal digits, which means we have up to 12 bits, which we can handle. 1 FFF has exactly 13 bits. You're right. Okay. So 1FFF can indeed be done because those are all ones. So we have 13 bits of ones in this case. All right. But you can see that nothing is happening, because the RAM component is not even selected. It's not really paying attention. The reason why I can inject a value is only because of Logisim, because of the interface of Logisim. I can just type it in like that. Okay. If you want to access any one of the other locations, because it's not shown here, once again, go right-click on it, go to Edit Content, and now we have, quite a bit more locations, because the last location is 3FF, which is 1023 in decimal. Okay? Are we doing okay so far with how to work with a RAM component? We good? All right. So let's just say that we want to read that location back, okay? How do we do that? Well, first of all, we have to specify that location at the A port, okay? So what location are we talking about? This is 004, this is 005, okay? How do I express 005 using 10 bits? Okay, what is 5 in the binary? 101, very good. So all the most significant bits are zeros except for 101 as the least significant 3 bits, okay? But nothing is happening, why? Because the RAM component is not even selected. It's not paying attention, it is not enabled. So that's the other thing we have to do is to say, hey, I need you to wake up and pay attention. And you can see as soon as the select pin is selected, whatever I specify here at the A port is now specifying what location in RAM is selected. It is now highlighted, which means it is selected, okay? Nothing is coming out of the D port. Well, that's because the LD pin, if it is a 1, it is specifying a read operation. When I specify a read operation, we are reading from RAM. Right now, it has a 0, which means we are proposing that we are writing to RAM, which is not what we want, okay? We want to read from RAM. So the other thing we have to do now is to put a 1 here, and you can see as soon as we turn the LD pin into a 1, which specifies a read operation, the output, which is the D port at this point, becomes all ones, because that's what we specified with 1FFF. That's 13 ones. So that's how we read a location in RAM. Do we have any questions about what we have just done here? Yep.
Can you explain how 101 is the address of 4 5?
Of 5, not 4, 5. It's exactly just 5.
Oh, okay.
Yeah. Yep, exactly. So it's just 5. Okay. Any other questions? Are we all good? All right. So let's go ahead and see how we can write to a location in RAM, okay? So before we do that, I'm going to turn off everything, because to do that, I kind of have to disconnect this component here. Nope, I don't need to do that. I can just put another input pin, which has exactly 13 data bits, because it has to match the width of the D port. Okay. And I also want the facing to be west. Okay. And there's nothing wrong with this hookup here, except for something that we're going to do later. Okay. So right now it's okay. You can hook up an input pin directly to an output pin, which basically is just doing nothing. Okay. So let's go ahead and try to overwrite some locations with a particular value. So I'm going to write, what I propose to do here. Okay, so I want to change. I'm going to use this kind of special notation here, RAM, treat it as an array, and I'll just say that I want to change location 0x. Let's see, we got 3 bits, so it can go all the way up to 7. So let's say 5, 3D. And I want to change the content at that location to say, oh, I don't have that many bits, sorry. Because I only got 10 bits, so that means I have 2.5 digits. I can do a 2F4, okay? So 2F4 is the location I want to change in hexadecimal. And the new content at that location is, I can specify up to 13 bits. So let's specify 0x FED, okay? All right, so this is what I want to do. The question is, how do we do it? Well, it looks like the first thing we need to do is to specify that location. So now the question is, which number do I present to the A port? Do I present 2F4 to the A port, or do I present FED as a hexadecimal number to the A port? Exactly, 2F4, okay? Because using the array indexing notation, that is how you select which element in the array to change or to access. So in this case, that's what we need to do. But 2F4 is a hexadecimal number. This only allows us to enter binary numbers. So we just have to do it step by step. The 4 is 0, 1, 0, 0. So now we have the 0, 1, 0, 0. The F is basically all ones. So we got 1, 1, 1, 1. And then the most significant 2 is just 1, 0. So now we have that. Are we doing okay so far with that conversion? Converting from hexadecimal back to binary? Okay. Each hexadecimal digit corresponds to 4 binary digits. So the conversion process should start with the least significant digits, and you work your way to the more significant digits. All right, so we got that. And we might as well also specify the content that is supposed to get into that location, which is FED, okay? So we start with D first. D is 1, 1, 0, 1. So we have 1, 1, 0, 1. And then we have the E, which is 1, 1, 1, 0. So we got 1, 1, 1, 0. And then we got the F, which is all ones. So 1, 2, 3, 4. So we got all of those. But nothing is happening. What is going on? Well, first of all, the RAM has not even been selected. In other words, all this time, the RAM component is not paying attention at all. Even though we are doing something with the A port and we are actually doing something with the D port, the RAM component is sleeping. It's taking a nap. Okay? It's not paying attention at all. So the first thing we need to do is to say, hey, wake up. We need you to do something. So you can see how it's going to the location right away, because as soon as it woke up, it goes like, okay, which page or which location am I supposed to be looking at? Oh, location 2F4. Okay, let's go there. Okay? And it's also paying attention to the other pins too. So the LD pin says, you're supposed to be doing a write operation. We're supposed to be overwriting the content at one location. To be more specific, we're supposed to be overwriting the content at location 2F4 with whatever is presented on the data port. Then you go like, but 0000 is not what we agree on, okay? We're supposed to be changing that to FED. How come nothing is happening? Because it needs a clock, okay? So the update of RAM content is the same thing as the update of an edge-sensitive D flip-flop. It's waiting for a rising edge on the clock port. And right now the clock port is static. It just has a 0, okay? So what we need to do now is to say, okay, let's give it a rising edge clock. So by clicking on the clock pin, now we have a rising edge, and right at the moment of the rising edge, it captures whatever is presented to the data port and store that internally to the location already addressed by the A port. And therefore, it completes the operation. So are we good so far with how the RAM components operate? Yes?
Where did the FED come from?
Say that one more time. The FED? The FED is what I want, okay? Because that states what I want to do, and FED translates to that. That process we have talked about already, how to translate between binary and hexadecimal. And some calculators can do that too. So, any other questions? Yep.
So LD overrides what's in the RAM?
So LD specifies the direction of operation. If LD is a 1, it is a read operation, which means we are reading from RAM. So the RAM data port becomes an output port. When LD is a 0, it specifies a write operation, which means we are trying to overwrite a location in RAM. So the data port now becomes an input port so that we can specify the new content at that location. Yep. Go ahead.
So, I wasn't really paying attention, I'm sorry. So you just said
I'm turning on your select port now.
when you said LD1, that means that we're reading from the address and I'll put it on the...
When LD is 1, we are reading from the RAM component. When LD is a 0, we are writing to the RAM component. But it is relevant only if the RAM is selected.
Wouldn't the load make more sense instead of putting LD to RW or
Yes.
IO?
Yes, it does. In most chips, actually has read write as the label, RDWR as the label, and I have no idea why Logisim chose to use LD as the symbol. Yep.
I don't know. In my circuits class, we talked about the load a lot. It has to do with the resistors and stuff. So that's probably where it's going.
Well, in electrical design, in a circuit design, the load basically refers to whatever you're switching. Yeah. So, but this is a different kind of load. Are we doing okay so far with these concepts? How to operate a RAM module? Okay. So let's go take a look at a ROM module. Okay. You guys will go like, oh, okay, that's easy. The reason why a ROM module is easy, okay, ROM test, okay, is, well, let's just take a look at the ROM module first, okay. This is a ROM module. Does it resemble a RAM module to a certain extent? It has an A port, has a D port, right? But it looks easier. It has a select port, which means, the RAM module can be sleeping, okay? It can be dozing off. But it doesn't have all of the other pins. It doesn't have a clock pin, doesn't have a load pin, and does not have a clear pin either. Why not? What does ROM stand for? Read-only memory. Well, if it's read-only, does it make sense that we want to specify the write operation? Nope. If a write operation is irrelevant, does it make sense to have a clock connected to it? Nope. Does it make sense to have a clear line to hook up to it so we can clear the content of ROM? Nope. So that's why those pins, that's why those ports are completely missing. Other than that, it works exactly the same way as a RAM module. Okay, you wake it up, doing the select, you present the address of the location you want to access to the A port, and then the D port will output the actual content at the addressed location. That's it. So do we have any questions about the operation of a ROM module instead of RAM module? No questions? All right. So if there are no questions about this, we go back to this because now we know what this part is doing, and we also know what this part is doing. So there's a ROM and there's a RAM here. They serve entirely different purposes, okay? Because I know some of you put computers together or you work with cell phones and you kind of go like, oh, okay, I understand RAM is the portion where you actually run the applications, but the ROM is where you store the image of the operating system so it cannot be corrupted or it doesn't go away when you power down your cell phone or your computer. That's actually not what is going on here, okay? This ROM serves an entirely different purpose. So do not stick with that mindset looking at the toy processor, okay? All right, so let's go ahead and look at some other stuff in here and see if we understand what this whole thing, or at least the components are doing. We got a lot of MUXes here, okay? These are called multiplexers. So what a multiplexer is really easy, okay? How many of you have watched Thomas Train, or what is the name of that children's show? Thomas the Tank Engine, that's it, okay. So if you have watched that show, you have seen, the tracks, switching, right? That's basically what it is. It's basically a switch. In the case of a MUX or multiplexer, it has multiple input pins and one single output pin, and then there's a selection to basically specify which one of the input connects to the output. At any time, only up to one input can connect to the output in a multiplexer. Okay? I still don't know what you're talking about. Well, let's go to the library reference, right? So this belongs to the plexer, library, and when you go to the multiplexer, it gives you the full explanation of what it is, how it operates, and how to control it. Okay, which is kind of abstract. So the best way to look at this is really to just think of Thomas the Tank Engine. You have your several tracks going in. Okay, you only have one track going out. Okay, so you need a mechanism and say, okay, this is the track going out, but which incoming track does it connect to? That is a multiplexer. So are we good so far? Okay. So let's look at another component then. So there's a MUX. There are quite a few MUXes around, and here's a DMUX. A demultiplexer. What do you think a demultiplexer does? I mean, you got multiplexer and get a demultiplexer. What do you think that D is going to do? Switches the direction around. Okay. So with a demultiplexer, it has one input line, it has multiple output lines, and then it has a select to basically say which one of the output line is connected to the input line. That's all it does. It's the reverse of a multiplexer. Yes? It has one input, one incoming line, multiple outgoing lines, and then there's a select line to basically say which one of the incoming line is connected to the one single outgoing line. It is directional. Unlike on a train track where things are not directional, when you're talking about electrical circuits, most things are directional. So a demultiplexer has multiple input, one input and multiple outputs, and then the multiplexer has multiple inputs and one single output. That's the only difference. So are we okay so far with what a multiplexer is and what a demultiplexer is? Yes?
So if someone that's not really familiar with this, are these components made up of internal things like AND gates and NAND?
Yes. So internally, it's a whole bunch of AND gates and OR gates and NOT gates.
And this is just offered completely through logic, and you don't have to.
Correct. Yeah. So these are built out of parts that are pulled out of Logisim directly.
Would you be able to examine the internal from logic?
No, but you can probably find references of how they're actually designed. I can explain certain parts of it too, if that is what you want. Okay. Yep.
What are the lines connecting to the bottom of them?
Say that one more time.
What are the lines connecting to the bottom of them?
The bottom? You mean this one?
Yeah.
That's the select. Because, okay, so just imagine that you have a switch, right, at a railroad. So you got, in this case, you have one track coming in, you have 4 tracks going out. But somebody has to say, should I connect to the first, second, third, or fourth, right? That is the control signal. So what I'm highlighting here, or what I'm pointing at here, that's the control signal to basically say, which track should I connect? Which outgoing track should I connect to the incoming track? That is what that line is going to do. So obviously there's a connection between the number of lines going out and the width of the control line. So in this case, what do you think is going to be the bit width of this control line? We got 4 outputs, so we have to be able to select one of the 4 outputs. How many bits do I need to use to select 1 out of 4? 2, very good. So it is in fact a 2-bit wide control line, because 0, 0 would select the first line, 0, 1 would select the second line, 1, 0 would select the third line, and then 1, 1 would select the last or the fourth line. Is that okay? Does that explain what that line is? Okay, good. Any other component we haven't seen before? I think we have seen most of those, right? So there's just a lot of multiplexers, This is an OR gate. We have seen that already. This is another multiplexer, tons of tunnels. Yep.
What are those like grades and number things?
Hmm?
Like those gray squares with numbers in them?
This one? That's a constant. Yep, so that's just a constant. Okay, good point.
What's the piece just to the right of that has 00, DQ, and
Oh, that's a register. Okay. So this is where we left off from the last lecture from on Tuesday. Remember on Tuesday, I said, oh, if you hook up 8 of those, level, edge sensitive, resettable, and there's one more thing about it. I cannot remember what it was. Clocked, D flip-flop, and you hook them up, and they all share the same control lines, but they do not share the actual data line. That's how we look at it from the outside. So the D port is the input into the whole thing. So it is 8-bit wide. Q is the output, also 8-bit wide. EN is the level sensitive enable. This little triangle thing is the clock, okay? That's where we hook up the clock line. And then the last one, which has a 0, that's our clear, which is the reset line. So that's a good question, but that's basically what we talked about on Tuesday. And you can see we have quite a few registers. So this is one register called flags. We got another register down here called the instruction register. And then we have another register to the left called the program counter. That's also a register. And then down here we have a microcode pointer, which is yet another register. So we got a whole bunch of registers, within the design. Okay. Yes.
What's that CNCL? Is it like a normal ladder?
Which part of the picture are we looking at?
On the left.
On the left. Top left. C. Oh, this one? Oh, you're going to like this one. It's an adder. So you don't have to implement your own carry look ahead adder. It's done for you. Okay? All you have to do is to specify how wide it is. So this one is an 8-bit wide adder. So the reason why it has so many pins is because these two are the numbers that you want to add. This is carry in, K0, okay? K0 in our discussion is carry in. K8 is our carry out, and this is our sum. So those things, all the symbols that we talked about in the past, well, they're all kind of coming back, right? So let me just repeat that, a little bit. This is our X, this is our Y.
Can you zoom in?
Huh?
Can you zoom in?
I can certainly do that. So this is our X, this is our Y, this is our K0, which is the carry bit that is coming into the system. This is carry out, which is our K8 in this case, because the carry to bit 8 is not going to be stored internally. And this is our S, the sum. Yep.
Why is there a constant to it?
Why is there a constant to one of the inputs? Because this adder only has a simple job to perform. Add 1. That's all it needs to do. Day in and day out, that's all it's going to do is just add 1. Do we add 1 or not? That's all it does. It's a part of a circuit that makes a counter. Click counts 1. Click counts 1. Yep.
So that's why the CL is not connected anywhere?
Well, C out is not connected anywhere. That is correct. But the sum is. The sum actually has a path to go back to the program counter, so we can auto increment the program counter. Very good. So anything else that we do not recognize? Oh, I find a few things that we don't recognize. Hey, this thing here, this whole thing we don't recognize. Well, that's because it is a component that is actually like this. So you look at this and go like, what is that? Well, okay, so we do it step by step, right? There's an input, register input, which is an 8-bit input pin, okay? This is a decoder. So a decoder is just like a demultiplexer. No. Single input, multiple output, yes, it's a demultiplexer. It's just like a demultiplexer, except the input is always a 1. Okay? So the way it works is whatever you specify here, whatever you select, okay, the corresponding output pin is going to be a 1. So if I say, 0, 0 here, and I enable it, then output 0 will become a 1. If I say 1, 0 here, then output 1, 0, which is the third output, is going to be a 1. It is called a decoder. So let's see how this thing works, okay? So you present, some data. If you want to update one of these 4 registers, okay, the way you do it is you present the data that you want to, the new data that you want to overwrite, in the register, and then you use this to specify which register you want to change, and then you do a clock, which is a global, signal, and that will update that particular register. Do you guys want to see how the register bank operates on its own? Okay. So we can do that. And the way to do it is just to open the register bank component on its own. Okay, so now we can experiment with this. So let's just, okay, which register do you want me to change? Just pick one, A, B, C, or D. Huh? B, okay, so let's just change register B. So register B is known as register B, but it is also 0, 1, because it is the second in 4, right? So we have to specify 0, 1 here. And what do you want to change the content of register B to? Give me the hexadecimal number. FF? Okay, well, we'll change it to FF, which is all ones, right? So we flip all of these to 1s with the input port here. And you say, but nothing is happening. Well, that's because the decoder is disabled. So the next thing we need to do is to turn on the decoder. So you can see as soon as we turn on the decoder, it takes these 2 numbers to select which one of the output pin would become a 1. And now it is saying, hey, register B, pay attention, you're enabled. Is that okay? Now, the input pin we know as register input is multi-dropped. See how this is connected to register A, B, C, and D. So they're all listening to register input as an input pin, but only one register is paying attention. The other 3 registers are like, they're all dozing off, right? So nobody's paying attention except for register B in this case. So what else do I need to do in order to update register B? The clock, right? We need a rising edge at the clock. So now we say, okay, clock line goes from 0 to 1, which makes a rising edge, and now register B is changed. Okay? So this is basically, I call this a register bank because it is a collection of multiple registers. And these registers are quote unquote software accessible registers. So your code, your opcode can directly say, I want register A here, I want register B here, I want to update register C over here, and so on. So these are software accessible registers, whereas the other registers, you really don't have direct access to those. Okay? All right, so that kind of explains how to update a register. So let's turn this off. Okay. What about the output? What do we do with the output of these registers? You can see how the output of each register go to both of these multiplexers. They don't just go to one, they go to both output registers. Multiplexers. And then each multiplexer has its own select pin or select signal. So this way, this output can connect to any one of the 4 registers, and this output can also connect to any one of the 4 registers. And they are completely independent. If I want to, both of the output pins can connect to the same register if that is what I want. Is that okay? Do we have any questions? Yes? Why do we have 2? Okay, so I will save your question first. I'll push it on the stack and then, yeah.
My question was, the clock doesn't have anything to do with the output then, does it?
No, the output does not need a clock. Clocks are only needed for inputs when you're updating something. So I pop that item from the stack, and now we'll get back to your question. My stack is pretty shallow, so yeah, once I have 3 or more items, I start to lose items on the stack. So now I get back to your question. We need 2 because for addition, you need 2 numbers. For subtraction, you need 2 numbers. So most of the operations we want to perform need 2 numbers, and those numbers come from the register bank. Okay, very good question. Yep.
Okay, what's the difference between those register out with A, B, C, D?
Each output, register output 0, can connect to any one of the 4 registers. And then register output 1 can also connect to any one of the 4 registers.
The A, B, C can only go one direction?
Say that one more time.
The A, B, C, D can go only one direction? Or they,
Well, the Q is the output of the registers, so that can only serve as an output.
an output? So those A, B, C, D are outputs
On top? Oh, you mean these? Okay, so the reason why we have those A, B, C, and D's as output pins is for logging purposes. This allows us to log the status of the processor at any time. So we'll get to that part when we get to that part. It allows you to debug your program, hopefully more easily. So they're only for debugging purposes. They don't really do anything actively. Okay. Are there any other questions about the register bank? Now you asked a very good question. Okay. Why do we have 2 outputs, from the register bank? And the answer was, well, when we need to add, subtract, and do stuff like that, we need 2 operands, right? So now the next question, logically, the next question is, where do we do all those calculations? Okay, so let's close that. And we'll go back to the main design. So all of those calculations go into this seemingly simple little thing that has like 1, 2, 3, 4, 7 ports, okay? So what is this thing? This is called the ALU. The ALU stands for Arithmetic and Logic Unit, okay? So let's go ahead and go in and see what it looks like in the inside. And you'll go like, that doesn't look too bad. Oh, there's a little more, yeah. Okay, so let's take a look at the basic design of the ALU, the Arithmetic and Logic Unit, okay? In 1 and in 2, now this is bad naming on my part. I should have named those in 0 and in 1, to be consistent and always start counting from 0. But let's just stick with this one, okay? In 1 and in 2. They specify the 2 numbers for any operation, okay? So now we have these boxes in the inside here that can perform different operations. So we have an adder, okay? This is an adder. If you click on it, it will tell you what it is. This is a subtractor. So with a subtractor, we have, this is X, this is Y, this is B0, this is B8, and this is D. Okay, so those are the letters that we used when we talked about the carry look ahead and the borrow look ahead mechanisms. Okay, so this is a subtractor. This is a bit shifter. So it allows you to bit shift, to the right-hand side. There's no left shift. Yes?
Is there a reason they use an adder and a subtractor and not one that just can switch to both?
That's because LogicSim doesn't give me an option. and I'm too lazy to make a 8-bit carry look ahead adder for slightly obvious reasons. This is a negator, okay? So, but it's an 8-bit wide negator. It negates all 8 bits. It's a bitwise NOT operator. This is bitwise AND. This is bitwise OR. So these are representing all the basic calculation support that we have. This is it. Okay, it cannot do multiplication, not without software. Okay, it cannot do multiplication or division without actually coding it. But this gives us all the basic stuff that we need to implement multiplication, division, and all the difficult math stuff that we need to do. Well, if that is the case, how do we send the inputs into the correct operation? We have these demultiplexers to do the job for us. So remember, a demultiplexer has one input and multiple outputs, right? So when you look at the outputs of the demultiplexer, what do you see? You can see that one goes into the adder, one goes to the subtractor, one goes to the shifter, right shifter, one goes to the bitwise NOT, one goes to the bitwise AND, and one goes to the bitwise OR. But how do we know which way to send it? Well, the selection, which is done by a pin right here. So this is OPSEL, which stands for Operation Select. It is 3-bit wide so that we can select up to 8 operations. So even though we only have 6 used, so that means we have room for 2 more operations if we need to. Is that okay? What about the output? Okay, when we are done with an operation, how do we send the output, of the operation out of the ALU itself? So you can see the output of the adder, the output of the subtractor, the output of the bit shifter, the output of the bitwise NOT, the output of the bitwise AND, and the output of the bitwise OR. They go into a multiplexer, which has multiple input and only one single output, right? But when you look at the selection of this multiplexer, it is exactly the same thing as OP-cell. So it basically is just a whole network of multiplexers and demultiplexers so that we can send the inputs to the right operation and then take the output of that operation and present it to the output of the ALU itself. So if this is pretty much all we need to do, what is the rest of the circuit, right? Well, those are the flag stuff, okay? I hope you guys still remember the flags. Yes? Okay. So the easiest one to explain is the S flag, the sign flag. This is the sign flag. What is it doing? How does the sign flag connect to the output of this multiplexer? What is the name of the component that is sitting between here and here? What is this thing? It's a splitter, right? Except it's a very deformed splitter because all it does is to get bit 7, which is the most significant bit, and send it out to sign out, okay? That's our sign flag. Does that match what you have learned about the sign flag? Okay, cool. The next one that is also somewhat easy to explain is the Z flag, okay? We never really quite used the Z flag before, but basically the Z flag is a 1 if and only if the output of an operation is a 0. Let me say that one more time. If and only if the output of an operation is a 0, the Z flag becomes a 1, okay? So how do we make it happen? This is how we do it. We take a splitter, split all 8 bits into individual wires, okay, individual bits. Get them all through a NOR gate. Okay, this is a negated OR gate. So if at least one of these is a 1, then the OR is going to be a 1. But since this is a NOR, the NOR becomes a 0. So the only time the NOR gate will output a 1 is when all inputs are zeros. So this is how we detect whether the result of an operation is 0 or not. Are we good? Well, what about the overflow flag? I hope you guys still remember the overflow flag. Yes? Okay. So the overflow flag needs to take a look at several things. So that's also why we have a splitter to split bit 7 of the first operand into S1. And we have another one for the second operand, which is S2. Okay. So those are corresponding to the most significant bit of the minuend, which is S1, the most significant bit of the subtrahend, which is S2, and we also need to look at the most significant bit of the difference, which is S out here. So all 3 will have to be going through some kind of gate logic to come up with the overflow bit. So that logic is right here. So if you focus on just this portion of the gates, this is how we compute the overflow using only logic gates. But it does match the equations that we talked about in class. So if that is the overflow, then what about this thing here? That is also the overflow, except one is the overflow, the one that I have clicked on right now is the overflow after an add operation. The one below is the overflow after a subtract operation. We didn't spend too much time to talk about overflow in the context of an addition, but it does make sense, right? If you add two non-negative numbers and you end up with a negative number, don't you think we have an overflow situation? And that's how it gets detected. The logic is about the same, except certain things are just kind of flipped around a little bit. Are we good? Okay. Oh, I also vaguely remember there's an L flag, right? Which is the exclusive OR between the overflow and the sign flag. Where is that? It's right here. So we take the sign flag, we take the overflow flag, and then we do exclusive OR, and that becomes the L flag. Okay? So the ALU not only contains all the logic to perform arithmetic and logical operations, but it also has the logic to set and clear the flags that we have already talked about. The next question then is, what are we doing with those flag bits? So we go back to the main processor design, and we look at the flag out. Okay, this is flags out. Okay, I'm already using the poke tool. It should be poking it. There we go. It does report an error, but that's only because the result is undetermined. That's what it's reporting. It goes into a flags register. In other words, after you add numbers, after you subtract numbers, after you bit shift numbers, after you do a bitwise OR, bitwise NOT, and stuff like that, the flags are actually remembered in a register, so that we can use that later on for really fun stuff. Okay. But at this point, we'll just say that, yeah, we can remember that. So do we have any questions about the basic architecture of the processor? Are there any components that I have not explained yet in this entire picture? I think I got them all. So that means we are done with this semester, right? I mean, this is it. Okay. So now the question is, but how does the processor work, right? How do we add a number and put the value or the result of the addition back into a register, for instance? How do we go to RAM, a certain RAM location, grab a byte, put it into a register? So those are the questions that we need to kind of answer, okay? All right. So do you guys still remember what is a von Neumann architecture and what his contribution was? What was John's contribution? What was it? To have RAM, to have memory, to remember, to specify the instructions, okay, to tell the computer what to do. That is the key, okay? So we can store instructions in RAM, okay, which in return will control all this mess here to perform addition, subtraction, comparison. Oh, let's go ahead and store the result over here. Oh, let's go here to grab another byte to process. That is the idea. We store the instructions here, use the rest of the processor to perform the actual operations. Okay? Then what about that ROM down here? Okay? If the RAM is specifying what operations to perform, what is the purpose of this ROM? Now, whatever we store in this ROM, these are called microcode. I call these microcode slices. Okay, some people just call it microcode, but I like to refer to each location as one slice of microcode. Okay, let's just look at the picture here. Okay, do you see how? Okay, let me click on it so you can see the width of the data port of this particular ROM module. What is the width of this ROM module? 26. Okay, which is a very odd, strange number. Okay, 26 bits as the output, which corresponds to what we are seeing right here. Do you see how it goes into a splitter, split into like a whole bunch of stuff? and then one of the split end, split into further, like a whole bunch more stuff, right? I mean, I just use a whole bunch of tunnels. And those tunnels go into individual components of the rest of the processor. This is really the heart of the entire processor. Okay? These bits here that we specify, they tell the process, the rest of the processor, should I connect this register to this input of the ALU? Should I connect the output of the ALU back into the register bank? Should I connect this program counter to the address port of RAM? And where should I connect the data port of RAM? It's all up to these individual bits to specify. Are we having a general idea what this is? Yep, go ahead.
It's like a bias of the processor.
This is what?
Like a bias of the processor.
It is kind of like a bias of the processor. These are individual operations. So what we see in software as in one instruction is not exactly individual when it comes to the internal operation of a processor. But when we see a single slice here, that is individual. At each time, at each click, it can only perform one of those operations. So that's the lowest level of operation. Okay? Okay, so in case this is a little bit abstract, which it is, okay, let's go ahead and look at some pictures so that you can kind of remember what the whole thing is. So we'll look up Thomas the Tank Engine. I mean, imagery is always good, right? So Thomas is a train, right, on the island of Sodor, okay? So on the island of Sodor, which we see as a processor, and Thomas is a train, which means it is a transportation of information, bits, and data, okay? This is how we connect components. So Thomas the Tank Engine will carry the bits from the register bank to the input of the ALU, okay, which is a factory of sorts, right? And then Percy, another train, will carry another operand to the other input of the ALU, okay? And then the ALU, which is the factory, will operate and create a result, right? So the result is going to be carried by Henry, yet another train, another tank engine, back to the depot so that it can be stored. So the trains individually are basically mechanisms of moving bits around inside the processor. Are we good so far? Okay. So the next picture you need to look at is the island of Sodor. Okay. And here's a map of the island of Sodor. And let's see, which one should I use? I want one that shows, oh, this is a good one. It's open for business. And where is the bitmap? No. I suppose I can just right click and open the image in a new tab. There we go. All right, so this is the island of Sodor, which is the processor, right? So this is the entire processor. We got train tracks all over the place. And at some of these places, we got 4 tracks going in and only 1 track going out. And at some other locations, we got 1 track coming out and multiple tracks going, 1 track going in and multiple tracks going out and vice versa, okay? What do those things correspond to? Multiplexers and demultiplexers, okay? Okay, so we kind of have a general idea of what things are now, right? So if you look at the result or the output of a factory as actual things to store, then what is our warehouse? What is equivalent to a warehouse on this island where we can kind of store things that are already processed, and then sometimes we can go there and grab things to be reprocessed? RAM, exactly. So we got a component somewhere here that is the warehouse, which is RAM, okay? Cool. But without someone to control the tracks, like which one connects and when to connect the tracks and stuff like that, we would have major accidents, right? And we wouldn't want that. That would upset all the tank engines. We don't care about the diesel engines. But the tank engines, we do care. We don't want them to run into each other, right? So who else is a key component in this entire picture that makes sure that everything runs smoothly and efficiently? The controller. The controller has a name. That's not politically correct anymore. Sir Topham Hatt is the proper name. So now we have Sir Topham Hatt, which is the controller. Okay, so his job is what? What is this guy's job? He's the one, in the controller office, and he would say, "Oh, I need this, switch to go this way and connect, Thomas the train from this factory all the way to that, depot, and I need to control this track here, so the Henry has a way to go from here back to the warehouse, and I need to control this track here, to control this switch, of this track, so that Percy, has a way to go from here to wherever he's supposed to go." That's his job. Okay, that's the controller. He is the one who is orchestrating the entire thing by controlling those individual control bits of the multiplexers, demultiplexers, enable pins, and so on. Okay. We're missing still one last component, okay? Timing, okay? What is the time? Who keeps track of the time of the entire island of Sodar? There's a clock signal, okay? The clock signal is universal to every single component of the processor. So that one, I don't really have a picture. It's kind of hard to find a picture to represent that. But if you click on the clock pin, you will see that it is shared by all components. So this is the clock pin of the microcode pointer, but it is also going into, guess what? Going into RAM, going into the flags register, going into the program counter. It is going into the register bank. Okay, so every single register in the register bank uses this exact clock. So the entire island of Sodar uses a single clock, so that when we say, "Oh, Thomas is supposed to arrive at 1 o'clock, 1 p.m., it is 1 p.m. Okay, everybody understands what 1 p.m. means. Is that okay? So does that give you a general idea of the major components inside the processor? Okay. Yep. Say. ROM. So ROM is the script that Sir Topham Hatt is following in order to operate the whole thing.
I noticed that there's multiple bits.
Yes.
I don't know, which
Okay, so imagine that I am Sir Topham Hatt. Okay, I kind of have his figure, has his physique. So I'm Sir Topham Hatt. I'm not quite that bald yet. I'm getting there. So in front of me is the control system for the entire island of Sodar. Okay, what do you think I'll be seeing? I'll be seeing a lot of switches, right? But each switch is no more than a binary bit pattern. Okay, so I got these 2 bits controlling a 4-input multiplexer. I got these 3 bits controlling the output of a 8-output demultiplexer. I got the enable pin of the RAM. I got the enable pin of the ALU itself, and so on and so forth. So this is my panel. And every single individual switch is binary because it's either a 0 or 1. Does it make sense? So if I look at my daily routine, which is stored in RAM, okay, and it says, "Oh, we need more coal," okay? How do I get more coal? How do I get the trains to connect in a way that they can go to the coal mine, pick up the coal, get back into the coal, wherever we store the coal, and deposit it? I look at the script. So the script says, okay, flip the switches in this particular way. and then the train tracks, the switches, the enable of the mine, and the enable pin of the warehouse will be set up correctly. Those are the bits in the ROM. So the ROM is basically what Sir is using to configure all the switches, to configure all the enable pins, to configure whether we are reading from RAM or we're writing to RAM and stuff like that. So all of these bits that we have stored here, 26 bits, okay, for each slice of time, is basically controlling each individual zeros and ones so that I can get all the switches done correctly. I can set up, the factory should be enabled by the time the train arrives, or the gate over here should be open by the time the train leaves, blah, 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 blah. And that's how operations are performed. Is that okay? I think I should do, I think I have to subcontract the design hub to make a short animation with the tank engines carrying zeros and ones around. That would make an awesome, like an educational movie. It might infringe on some copyrights though. Yeah, yeah.
Can you call it the brain of the processor or not?
No, well, okay. So it's sort of the brain of the processor, but by itself it doesn't know what to do. So the script comes from RAM. So the RAM component is what is actually supplying the overall operation. Like, if there's insufficient coal, go to the coal mine. If there's sufficient coal, go ahead and perform these operations. Go to the seaport or pick up some kids from the beach and stuff like that. Okay? So that's kind of the overall idea of the processor. Tonight's lab relates to the processor. Okay? Okay, so let's not leave just yet. Okay? The instructions inside the processor ROM, inside the RAM, they're all zeros and ones. Okay, so in other words, if the pattern that says, Thomas is supposed to go here and pick up something and then come back and drop it off over here, they're all specified in zeros and ones. And how well can you remember, 8-bit patterns? Not very well. Okay, so that means we need some other way so that we can translate into zeros and ones a little bit better, okay? That is the job of the assembler. Okay, so when we go here, so the questions down here will have like actual opcodes. So these are what we call mnemonics, which is a little bit better than zeros and ones, okay? I know they're still kind of cryptic. Load immediate is LDI, CMP is compare, ADD, okay, I don't think I have to explain that one. JCI is jump if the carry is set, okay? DEC is decrement, INC is increment, JMPI is jump immediate, halt is basically just halt. Well, I know they're still cryptic, but better than a whole bunch of zeros and ones. So these are called mnemonics, okay? They are basically words that we can more or less it's easier to remember and use, okay? But they need to be translated into the zeros and ones that the processor understands. That tool to do the translation from mnemonics into zeros and ones to the opcode is called the assembler. It is kind of like a compiler, except much simpler. How simple? I was able to turn a spreadsheet, a Google spreadsheet, into an assembler. That simple. So that's what you'll be using for the rest of the semester, is to use that spreadsheet as an assembler. You write code like this, put it into the spreadsheet, it translates everything into zeros and ones, you load the zeros and ones into RAM, and then you watch the program run. Yep.
Where's the assembler located?
The assembler is located in the same folder where you find everything else. And there are two versions of this, and you can use either one. This one, as the name implies, is to be phased out, so I would not start with this one. This one, it does work with, it has a lot of extensions compared to the other one. So I would start to use this one, which is assembler with postfix expressions. So that's the assembler that we'll be using this semester. So I'm running out of time, but for the purpose of your homework assignment, I think you guys got most of the concept stuff that you need to get started with the homework assignment. So I'll see you guys over at the lab, and we got stuff to do today. Yes, there's a code for it.